2.5 million light-years away, another galaxy drifts toward us, the Andromeda Galaxy. It's our nearest cosmic neighbour, and one day it will collide with the Milky Way. Tonight we begin a calm journey across that endless space. If you enjoy this voyage, please like, subscribe and share, and tell us in the comments, would you travel to Andromeda if you could? Thank you for watching. Now, let's begin. The backdrop is a quiet ocean of darkness, where islands of light drift in patterns too large for any single glance. Space seems empty, yet across immense reaches, galaxies gather into delicate webs and leave hollows like caverns between threads. In that hush, the local group sits as a modest archipelago, and within it a broad spiral begins to claim attention. It brightens thought more than it brightens the sky, because even as a soft smudge, the scale behind it is vast. The spiral is Andromeda, a nearby giant only by the standards of intergalactic space, a patient presence that steadies the mind before the approach begins. Large-scale structure sets the stage before any mirror tilts upward. Gravity draws matter into filaments, and along those filaments galaxies assemble, then fall into smaller bound groups. The local group is one such family led by two great spirals with many companions. Beyond it lies the sheet of nearby systems, and beyond that the slow flow toward richer clusters. Labels help, but the feeling that matters here is layered scale, each level enclosing the next like nested shells. Within this nested plan, Andromeda gains context as a keystone piece, rather than a solitary wonder. Light takes time to cross such expanses, and time becomes part of the scenery. The glow from Andromeda that reaches a mirror tonight began when early humans shaped careful stone along ancient coasts. For minds tuned to days and seasons, the idea that a glance gathers history carried on a beam is quietly disorienting. No sound travels across the gulf, yet information does, and its faintness preserves the patience of the journey. The background, therefore, is not just a place, it is a duration through which signals move, and every view is also a look into the past. The sky is more than black. The afterglow of the first light fills space like a cool and nearly uniform mist, rippled just enough to seed later structure. Upon that curtain, galaxies write the present. Some are narrow slashes seen edge on, some are round and diffuse, some carry the scars of close passages. In one direction a spiral larger on the sky than the full moon stretches as a pale flame. Under true darkness the unaided eye can sense its length, yet its low surface brightness insists that patience is part of the method. This backdrop also holds motion so coherent that it can be mistaken for stillness. Clouds of gas cool and settle inside halos of invisible mass. Stars switch on, shine, and age, returning enriched material to make the next generation. Clusters scatter, disks tilt and warp, and streams unwind like threads teased from old cloth. Everything moves, yet the pattern persists, and the persistence gives the night its calm. The serenity is not the absence of change. It is the result of change unfolding with patience across great spans. Set among peers, Andromeda gains meaning. A small irregular companion flickers with uneven starbirth. A giant elliptical nearby carries stars without a spiral's order. Far beyond, compact spirals crowd deep surveys like grains of salt. Against that diversity, Andromeda appears mature, a system that has endured encounters yet kept a disk and arms. Its calm on the sky is not the calm of inaction, but the calm of a pattern that persists, while parts exchange energy and place. The quiet face on the sky therefore hides a long memory of events. The attention that reveals this stage is patient more than forceful. Observers wait for air to still and for moisture to settle, then gather the weak arithmetic of photons. One exposure adds to another, until a surface brightness too shallow for a moment becomes a clear veil. Over seasons and years, suspicion becomes shape lanes of dust appear as soft strokes the outer disk as a faint oval halo, and a gentle skew that hints at tides raised by neighbours. What begins as a blur becomes a landscape of gradients. The cosmic backdrop is a field of relations. The Milky Way and Andromeda exchange a slow promise through their shared pull. Dwarf companions circle both, and streams stripped from those small galaxies span the space between as if sketching lines of force. The triangulum spiral hangs as a lightly built cousin, its own history of star birth written in blue knots and extended arms. Considered together, these elements replace the first impression of isolation with a web of influence that binds the local group. A deeper motion threads through the whole frame. The local group itself drifts through space with respect to that first light afterglow, following the pull of mass spread far beyond the nearest clusters. Within the group, the two dominant spirals fall toward one another, along a path that looks straight only because the scale is so large. Nothing here hurries, yet everything is underway, and that is the character of the backdrop. The quiet here is woven from many kinds of light. Starlight shapes the visible picture, but there is also the thin glow from warm dust, and the clean lines from excited gas that trace shocks and births. Deep images collect the near-invisible wash from old halos, while precise measurements of variable stars mark distance like mileposts. By choosing bands that let one thread stand and others recede, observers assemble a composite that is less a portrait than a record of behaviour. In that record, Andromeda becomes a hierarchy of components whose relations set the tone for what will be found inward. The backdrop is also not empty of questions. Faint asymmetries in the distribution of satellites suggest long interactions that models do not yet capture in full. Subtle warps in the outer gas point toward torques raised by companions that may already be stripped to threads. The presence of an extended halo whose mass far surpasses the light challenges intuition shaped by luminous matter. These clues do not break the calm so much as deepen it, because each clue implies duration and memory. Patience opens the scene even without instruments. With dark adaptation, the Andromeda smudge lengthens, and the idea of a spiral arrives before resolution. That faintness is not a failure of sight, but a statement about distance, and about how much starlight must be stacked across the gulf. The same patience in instruments turns suspicion into shape. Thickened outskirts appear uneven-laned of dust sharpen, and the whisper of streams glows faintly around the main disk. A blank sky becomes architecture once enough time is allowed to gather it. The backdrop ends where it began, with stillness that is not empty. In that stillness, a single spiral waits, neither declaring itself nor hiding, and its outline invites a closer approach. The next layers will move inward from this wide canvas to the family of galaxies, the dim outskirts of the halo, the streams and shells, the disk and arms, the clouds and nurseries, the ancient clusters, and then the central heights. For now, the work is simple. Hold the quiet long enough for the shape of the whole to sit clearly in the mind, and from that calm begin the approach to Andromeda without haste, a slow closing of distance measured not in steps but in understanding. A map takes shape from counts of faint galaxies, from long exposures that sift weak light out of noise, and from distance ladders built step by careful step until position gains depth and motion. What first looks like a random scattering becomes a family, the local group, a loose federation stretched across several million light-years and held together by gravity's patient grip. Two spirals anchor this family. One is the Milky Way with its barred heart and ring of companions. The other is Andromeda, broader in disk and more massive in its unseen halo, with its own swarm of attendants. Between and around them move dozens of dwarfs, some neat and smooth like featureless spheroidals, others ragged and irregular with patches of young blue stars. Off to one side, the triangulum spiral hangs as a lighter cousin whose path may be bound to Andromeda. The first task of cartography is to place these members in 3 dimensions. Variable stars with steady rhythms fix anchor distances. Bright giants and tip points in old stellar populations add further rungs to the ladder. Planetary nebulae and star clusters fill in intermediate markers. With these in hand, the group's outline gains thickness. Andromeda lies about 2.5 million light-years from the Milky Way, far enough that individual sun-like stars blend near enough that star clusters, dust lanes and outer streams can be charted. The triangulum spiral sits somewhat closer to Andromeda than to the Milky Way. Around both large spirals, companions gather in uneven shells, whose shapes already hint at past tides. Then comes motion. Radial velocities tell which members approach and which recede. Proper motions measured for a few bright systems by tracking tiny shifts across the sky over many years add sideways components. Together they reveal a slow choreography. Andromeda approaches the Milky Way along a path only slightly skewed from the line between their centres. The triangulum spiral carries a larger sideways speed, which complicates the question of whether it is a long-term satellite of Andromeda or a neighbour on a wide arc. Around Andromeda, certain companions stand out by proximity and by signs of strain. A compact elliptical hugs the great disk and shows an older metal-poor population. A slightly larger dwarf sits a bit farther out and displays faint shells and fans that suggest a recent close pass. Beyond these, a retinue of dwarf spheroidals and diffuse irregulars extends hundreds of thousands of light-years into the halo. Some retain gas and trace gentle star formation, others are quiescent, likely stripped by tides and by the hot medium that pervades large halos. Their orbits, reconstructed from line-of-sight speeds and from the geometry of the outer debris, do not look random. Many appear to gather into thin planes. One such plane seems to slice the halo like a tilted sheet with several dwarfs spaced along it, and perhaps sharing a common sense of rotation. Whether this is a long-lived fossil of an ancient infall or a passing arrangement that will disperse remains an open question. The Milky Way presents a similar situation. Its companions form at least one thin arrangement, and long stellar streams cross the sky like chalk lines that mark where small galaxies were unspooled. These parallels suggest that the processes that build such structures are common, perhaps tied to how gas and small halos flow along filaments before they fall into larger systems. Mapping demands attention to the faintest traces. Deep images around Andromeda reveal arcs, loops, and diffuse fans that wrap the outer regions. Their stars are mostly old and poor in heavy elements, a clue that they belong to smaller systems that were pulled apart and stirred into the halo. Some structures, however, contain younger stars and pockets of gas, which implies a different origin, perhaps mild compression of material drawn outward during past encounters. These ghostly features are not decoration. They are the tracks of orbits written in light, and they let the group's history and geometry be read at once. Dark matter, though unseen, sets the frame of the map as firmly as coastlines set the shape of a sea. In both Andromeda and the Milky Way, rotation stays far from the luminous centres. That behaviour implies extended halos whose masses exceed the visible content by large factors. Where the halos overlap in influence, the orbits of small galaxies bend accordingly, and the effective border between the two giants becomes a broad saddle rather than a sharp line. The overall centre of mass of the local group sits between the spirals somewhat closer to Andromeda, because it likely carries a larger dark halo. Dwarfs that wander near this saddle can feel both pulls and may change long-term allegiance over very long intervals. The triangulum spiral complicates the picture in a subtle way. If bound, its long orbit around Andromeda would occasionally bring it close enough to raise tides in the larger spiral's outer gas, a possible cause of the slight warp seen at large radius, and a likely driver of uneven star formation in certain sectors of the disk. If only loosely associated, its flybys would still leave signatures that fade slowly in gas and stellar motions. Either way, the map gains arrows that do not point to a single centre, but instead sketch a web of mutual influence. Composition shades the chart as surely as motion shapes it. Regions dominated by old stars with few heavy elements appear redder and smoother, and they tend to populate the halos and the spheroidal dwarfs. Regions rich in gas and young stars brighten in blue and show clean lines from excited hydrogen. Those tend to lie along spiral arms in irregular dwarfs and in certain knots within the outskirts where streams and gas flows meet. Around Andromeda, the southwestern outer disk displays an emphasis on star-forming complexes that may line up with the memory of a past pull. The Milky Way shows a mirrored variety, though our view from within makes its map harder to draw cleanly. The boundary of the local group is soft rather than hard. Beyond it lie other small associations, and beyond those the gravity of a nearby massive cluster draws matter along long ridges. Still, for the present purpose, the local group is a useful basin within which most members are held for many orbits. Drift with respect to the afterglow of the first light provides the broad current. Motions within the basin provide the eddies and confluences that matter for encounters and mergers. The intrigue of the map arises from its incompleteness. Each deeper exposure reveals a new filament that asks for an origin. Each refined motion revises a satellite's path and prompts a reconsideration of how planes of companions persist. The overlap of halos invites questions about identity itself for a small galaxy that feels two giants at once. Andromeda's role is simple and profound within this web. It is the largest node within reach, yet it is also only one part of a structure whose edges blur into larger flows. Seen whole, the local group becomes a stage on which Andromeda, the Milky Way triangulum, and their many companions play out a very slow exchange of energy and place. The map is therefore both a chart and a forecast, a record of where things are and a suggestion of where they drift. With this framework in mind, the approach can proceed inward from the broad geography of the group to the unseen envelope that surrounds Andromeda, where the first hints of the halo's reach will set the tone for everything that lies farther in. Long before instruments make fine maps, a soft patch in the northern sky enters human records as a faint cloud that does not change. It is barely more than a breath on the darkness, yet it persists with the seasons and invites a patient note in careful catalogues. Early telescopes bring no clear resolution, only a brighter blur with a denser core, and for a time the object sits in a category that sounds simple but hides uncertainty, a nebula, a cloud of light. Through the 17th and 18th centuries, lenses gain polish, and mirrors gain diameter, and attention gathers around the brighter nebulae that hold shape night after night. Lists appear so that comet hunters do not lose time chasing smudges that are not comets. In those lists, the Andromeda Nebula stands as a guide star of confusion, steady, extended and enticing. The 19th century stretches the reach of the eye by changing the eye itself. Photographic plates keep watch where vision tires and long exposures pour faint light into emulsion, until structure emerges that no direct gaze can sustain. Spiral form announces itself in several nebulae, and the Andromeda Nebula begins to show a broad oval with a brighter centre, an uneven shading as if lanes cross the disk. The term spiral does not solve the deeper question. Are these patterns small and near swirls of gas within the Milky Way, or are they great islands of stars beyond peers of the Milky Way spread through space? Spectroscopy adds a line of inquiry that touches motion. In the early years of the 20th century, careful measurements of star-like cores inside spiral nebulae reveal shifts in spectral lines that imply large speeds along the line of sight. The Andromeda Nebula shows a motion that is not small. It appears to approach the Sun at hundreds of kilometers per second. That scale of speed is difficult to reconcile with a small nearby cloud. It hints instead at a system with the mass to move freely through interstellar space rather than within it. Yet speed alone does not reveal distance. The story turns when a way to measure far light is placed in hand. Work built from the insight that certain stars vary with a pattern tied to their true brightness gives astronomers a tool. If one can find those variable stars inside a distant system, and if one can time their cycles and measure their apparent brightness on a plate, then distance can be drawn from the relation between period and power. The Hooker telescope on Mount Wilson with a mirror 100 inches across provides the needed reach and clarity. On its plates within the Andromeda Nebula's haze, stars brighten and fade with steady rhythm. With those cycles measured and the relation applied, the implied distance leaps well beyond the known size of the Milky Way. The Andromeda Nebula is not a small cloud at the edge of our star system. It is a galaxy in its own right, a vast assembly of stars, dust and gas. The word nebula begins to fade from this object, and the idea of island universes gains ground. The change is not just in labels, it is a widening of the stage. The Milky Way becomes one galaxy among many, and the Andromeda Galaxy becomes the nearest large neighbour with which the Milky Way shares a deep gravitational bond. The shift is quiet in its telling, but immense in its consequence. With distance set, the features on deep plates gain scale. Dust lanes that looked like gentle strokes now run across a disk measured in hundreds of thousands of light years. A bright core that once seemed like a star becomes a crowded central region, holding a mass that bends the paths of nearby stars into fast orbits. Knots of brightness scattered along soft arcs are not sparks in a small cloud, but star-forming regions that rival entire dwarf galaxies in extent. Globular clusters resolve on the plates as round, dense swarms, and their colours and magnitudes offer clues to the ages and chemical makeups of the outer halo. Even the faint outer wash that plates barely collect takes on meaning as a population of old, diffuse stars stirred by past mergers. Debate does not end with the first distances. Some argue about the size of the Milky Way, and whether the Andromeda result overshoots or undershoots the truth. The sky hosts a contest of interpretations, each shaped by the limits of the data and by the difficulty of correcting for dust within our own galaxy. Over time, the weight of measurement settles the scale. Refinements to the brightness of distance markers, corrections for absorption, and the inclusion of many variables across multiple regions bring the answer inward and outward until the range tightens. The Andromeda Galaxy sits at a distance of roughly 2.5 million light-years. That figure carries a margin of uncertainty that narrows across decades as new instruments collect cleaner light. A parallel current in the early 20th century uses spectra to map motion across many nebulae, and a pattern appears that most show a redwood shift as if space stretches between galaxies. The Andromeda Galaxy is a clear and notable exception with its approach speed. That exception does not disrupt the emerging picture of a general expansion. It demonstrates instead that local gravity can draw neighbours together, even as the larger fabric extends. The Andromeda case becomes a local anchor in a global field, a reminder that nearby dynamics can differ from the cosmic average, while still fitting within it. The photographic era continues to shape what is seen. Faster plates, better guiding, and more stable mounts lift the veil on low-surface brightness structures. Diffuse fans and faint loops appear around the Andromeda galaxy, and companions are found that had been too small or faint to mark on earlier charts. The galaxy's outer disk is shown to be broader than the high-surface brightness core suggests, and a warp becomes evident that hints at past encounters. Each gain in sensitivity adds a line to the story and raises a new question about origin. The transition from visual observation to photography also changes method, where an eye must choose where to look and for how long a plate waits and gathers without preference. Later in the quiet of a study, the record can be examined, compared and measured with tools that grow more precise year by year. That patience separates suspicion from pattern. A suspected lane becomes a mapped lane. A possible cluster becomes a catalogued cluster, with a measured colour and brightness, and a likely age. The Andromeda galaxy turns from a smudge into a structure with components that can be discussed with care. The first eyes that saw only cloud would not have guessed at the layered complexity now inferred, yet the first eyes did something essential. They began a chain of attention. When an object remains through time and when observers keep returning with better tools, a continuity of effort builds a portrait that no single night could produce. The Andromeda galaxy becomes an early proving ground for many techniques that later apply to farther systems, distance ladders, built from variable stars' surface, brightness fluctuations, counts of red giant branch stars, kinematic mapping from emission lines, and the recognition that dust does not only hide, but also guides by marking where gas flows and stars form. In this historical passage, mystery does not vanish. It grows more refined. Once the Andromeda galaxy is accepted as an island universe, the question shifts from what it is to how it assembled and how it behaves. The faint structures seen in deep photographs suggest that it has eaten smaller galaxies and absorbed their stars. The speed toward the Milky Way implies future change on a scale that early observers could not include in their charts. Even the central brightness that photographs coax from saturation leaves open the nature of the engine at the core. Later instruments will approach those puzzles, but the path that leads to them begins with patient watching, with silver salts, and glass, with a long exposure that lets a quiet smudge write its true size across a preserved field. By the time the photographic era matures, the Andromeda galaxy stands as both a neighbour and a standard. It is close enough that features can be resolved with care and far enough that it can be considered as a whole. It shapes methods across astronomy by offering a reachable example of nearly every large-scale galactic component. It hosts a rich halo, a populous system of globular clusters, a disk with spiral structure dust lanes that speak of gas dynamics, star-forming regions that test ideas about triggers a bulge whose profile can be matched against models, and a central mass that governs motions in the inner light. The shift from a cloud to a galaxy is therefore more than a reclassification. It is the opening of a path inward that future sections will follow deeper into the halo toward the streams and shells, and then to the disk where asymmetries and warps carry the memory of encounters that photographs first whispered into view. Distance turns a picture into a place. Without it, a galaxy is a bright fog on an empty pane. With its scale and time step forward and the fog resolves into a system whose light has travelled for millions of years. The method begins nearby with simple geometry. For the closest stars, tiny annual shifts against the far background give direct measure of how far away they are. Those shifts recorded with care and then with exquisite precision by modern instruments in space set the first rungs of a ladder. From those rungs, brightnesses can be calibrated for classes of stars whose own behaviors make them reliable markers. Among the most important are stars that throb with a steady rhythm. Their outer layers breathe in and out, and the period of this breathing links to their true power. Find such a star in a distant system, measure the length of its cycle, compare its apparent glow to its expected glow, and distance falls out of the ratio like a quiet solution. This relation, built from painstaking observation of nearby examples and anchored by direct geometric measures, turns time into a ruler. The Andromeda galaxy hosts many such variables. In its nearer fields, the crowding of light makes measurements difficult, because blends of faint stars masquerade as single brighter ones. Yet with long exposures and clean seeing, individual rhythmic stars can be isolated and timed. Their cycles, once recorded over weeks and months, yield distances that place Andromeda well beyond the borders of the Milky Way. That first result, achieved a century ago, has been revised and refined many times. Corrections for dust are crucial. Dust dims and reddens light, and both effects depend on wavelength. By measuring the same variable stars through several filters, and by modelling how dust in both galaxies alters the colours, astronomers recover the true brightness, and hence a cleaner distance. Composition matters as well. The relation between period and power shifts slightly with the amount of heavy elements in a star. Nearby anchors with different compositions, such as stars in the Large Magellanic Cloud and in the Milky Way, allow those shifts to be characterized. Modern parallax maps of those anchors tighten the calibration until distance to Andromeda can be stated with smaller margins of error. Variable stars are not the only rung. Old stars climb to a well-defined crest in brightness before they shed their outer layers. On a colour and brightness diagram, this crest forms a sharp edge. The apparent brightness of that edge, once corrected for dust and for modest population effects, offers another measure. Deep images of the Andromeda halo resolve enough old stars that this edge can be drawn with confidence in several fields, from outer streams to inner halo, and the resulting distances agree with those from rhythmic stars within their shared uncertainties. A third path uses the gentle mottling in the unresolved glow of old stellar populations. In nearby galaxies, this mottling decreases with distance, because more stars fall within a single patch of sky. By calibrating how the grain of the light changes with distance, in systems whose ranges are known, one can read distance from the texture of the glow itself. Applied to smooth regions of Andromeda's bulge and outer disk, this technique provides a check that is largely independent of the specific mix of young and old stars found in the spiral arms. Planetary nebulae, the brief shells that old medium-mass stars cast off near the end of their lives, add another handle. The brightest of these shells tend to reach a similar peak luminosity. A census of such shells in Andromeda, corrected for detection limits and for extinction, traces a curve whose bright edge can be matched to well-studied samples in nearer galaxies. The edge marks a standard candle that, while less sharp than the rhythm of variable stars, nonetheless supports the overall distance scale when averaged over many fields. On rarer occasions, nature provides a more geometric gift. When two stars in Andromeda pass in front of one another as seen from Earth, and when their orbit sizes and temperatures can be measured from spectra and light curves, distance follows from the combination of orbital scale and surface brightness. This method is demanding because it needs bright, well-separated systems with clean data. Yet several such binaries have been modelled, and their distances land close to the others. In the radio compact clouds hosting stimulated emission from specific molecules, sometimes trace orbits in circumnuclear regions. In a few galaxies, angular motions of these maser spots and their line-of-sight speeds have yielded near geometric distances. While such signals in Andromeda are not yet a primary rung, the method highlights how motion and geometry can work together to reach beyond the brightness ladder. Across all these approaches, systematic effects are the quiet threats. Crowding makes faint stars appear brighter than they are. Differential dust extinction changes from field to field. Stellar populations vary with radius, altering the assumptions built into standard candles. To guard against these measurements are taken in many places across the galaxy, in the outer halo, where fields are sparse in streams, where a distinct population dominates in the disk, where star formation is ongoing, and in the bulge where old stars crowd. Instruments in space remove most of the blur from the atmosphere, letting individual stars be resolved even against bright backgrounds. Long-time series ensure that rhythmic cycles are measured without aliasing. Cross-checks between methods reveal where one technique may be biased high or low. Over decades, the combined work has converged. The distance to the Andromeda galaxy settles near 2.5 million light-years, with current best values quoted to within a few percent. That precision matters because it sets the scale for every derived physical property. The galaxy's size on the sky turns into a physical diameter measured in hundreds of thousands of light-years. The mass implied by measured speeds of stars and gas becomes a number with clearer bounds. The time it will take for the Milky Way and Andromeda to intermingle becomes a timeline with smaller uncertainty. Even the luminosities of supernovae star-forming regions and ancient clusters within Andromeda rely on this distance for their physical interpretation. The intrigue remains because distance is not a single number that applies everywhere within the galaxy. Andromeda is tilted with respect to our line of sight. One side lies closer by tens of thousands of light-years than the other, and its halo extends still farther. Streams wrap in and out, carrying stars that sit above or below the plane. When a distance marker sits in a stream, its position along the stream matters. Thus, the very structure whose details we seek also complicates the measurement that sets the scale. The response is to sample widely and to build a three-dimensional map of distances within the system rather than a single mean value. Doing so reveals depth in the halo and confirms that some streams are not only wrapped around the galaxy on the sky, but also in radius. The most recent refinement comes from the union of space-based parallax maps of nearby anchors, infrared imaging that peers through dust with less loss, and precise period measurements for large samples of rhythmic stars spread across the disk and halo. Infrared light reduces the effect of dust. Parallax maps fix the absolute scale. Large samples smooth out local irregularities. Together, these shrink the error bars further and draw a distance ladder that feels less like a scaffold and more like a bridge. The outcome is a quiet confidence rather than finality. Every rung is an inference based on physical understanding that can itself be improved. New surveys will likely find fainter variables, cooler giants nearer the edge, and more eclipsing systems. They will refine dust maps and population models. They may uncover subtle differences in standard candles between environments that shift the scale by small amounts. In this way, distance remains both an answer and a question, a measured span and an invitation to measure again with clearer tools. With the yardstick firm enough to trust the approach, can continue inward toward the unseen envelope whose gravity shapes rotation and carves the paths of satellites. Distance has turned the soft smudge into a neighbor with known scale. The halo will turn that neighbor into a structure whose invisible mass outweighs what the eye can see, and whose reach extends far beyond the bright disk. The unseen takes command at the edge. Far beyond the bright disk of Andromeda, where starlight thins to a pale wash, and dust lanes give way to sparse old stars and solitary clusters, motions refuse to slow as quickly as the visible matter would allow. gas keeps circling at hundreds of kilometers per second, stars in the outskirts hold speeds that would carry them away if only the light counted, and small companion galaxies move on paths that imply they are bound to a mass larger than any tally of shining content. From these clues, the outline of an extended dark halo appears not as a picture, but as a requirement pressed into the numbers. It is a vast, roughly spherical envelope whose density declines with distance yet continues so far that the size of the galaxy must be reimagined. The reach of this halo is measured in hundreds of thousands of light years, and its mass outweighs all stars, gas and dust by a wide margin. The first signs come from rotation. Within the bright disk, stars and gas orbit faster as distance from the centre increases, then would be expected to slow if the mass that matters is concentrated where the light is. Instead, the curve of speed with radius flattens and keeps nearly flat far out. Andromeda follows this quiet defiance as clearly as the Milky Way does, and its curve remains high at radii, where the surface brightness is too low to hide enough matter in normal stars. The only way to allow such speeds without unbinding the outer disk is to add mass where there is little light. This extra mass must be extended rather than packed into the core, or else the speeds would fall sooner. The result is a halo that carries most of the galaxy's mass and shapes its outer dynamics. Streams in the halo sharpen the picture. As small galaxies fall in tides, draw out long ribbons of stars that wrap around Andromeda like faint scarves. The widths and curvatures of these streams act as test particles responding to the pull of the whole mass distribution. If the halo were very concentrated, the streams would bend more sharply. If the halo were very diffuse, they would sprawl differently. By matching the paths and thicknesses of several streams, models converge on halos that grow less dense with radius in a smooth way, and that may be somewhat elongated rather than perfectly round. The exact shape remains debated, with some evidence for a mild squashing along one axis, and hints that the shape may vary with distance from the centre. Satellites contribute further constraints. Dwarf companions move through the halo and feel both the tide from the central mass and the drag that arises from their wake in the sea of dark matter. Those effects can alter orbits over long times, pulling satellites inward and slowing them as they lose energy. The degree of this orbital decay depends on the halo's density and on the distribution of mass in both satellite and host. Observed positions and speeds of the inner dwarfs near Andromeda suggest a halo dense enough to hold them in place across many orbits, but not so dense that they plunge quickly to their ends. The presence of thin planes of satellites adds a twist, because if such planes persist, they may prefer certain halo shapes and histories, perhaps pointing to coherent infall along ancient filaments. Farther out measurements of the temperature and faint glow of rarefied gas hint at a hot atmosphere that fills much of the inner halo. This gas is thin and hot enough to shine softly in high-energy light, and it carries heavy elements made in stars and later expelled. The amount of this gas, combined with the mass in stars and in cold clouds, still falls short of the mass implied by motion. Yet the hot atmosphere matters because it can strip gas from small galaxies that plunge through it, quenching their star formation and leaving them as pale spheroidals. The presence of many gas-poor dwarfs near Andromeda is consistent with such stripping, and the rate at which this happens again depends on the density profile of the halo. Weak gravitational lensing offers a quiet statistical glimpse of the halo's total pull. Background galaxies seen behind Andromeda's outer regions are sheared and magnified by the mass in front, not enough to create dramatic arcs, but enough to skew shapes in a way that can be recovered by averaging over many lines of sight. This method does not rely on how stars behave and therefore cross-checks the inferences from rotation and from streams. The result supports a massive extended halo whose reach continues well beyond the bright disk. At the largest scales, the timing argument between Andromeda and the Milky Way provides an independent handle. The two giant spirals move toward one another today, yet they likely formed from material that expanded with the universe before gravity drew them together. The time since that beginning and their present separation and approach speed put limits on the combined mass of the pair. Those limits divided according to how each galaxy's own satellites and rotation behave suggest that Andromeda's halo may be somewhat more massive than that of the Milky Way. The exact ratio remains open, and different methods sometimes prefer different answers, but the broad picture holds that both halos are the dominant mass in their respective systems. The halo also carries memory. Its inner regions may be slightly more concentrated if the early assembly was quick and violent, and slightly less concentrated if growth was slower and smoother. Signatures of ancient mergers can linger as shells of stars at certain radii, or as changes in the thickness of the disk where tides once flexed it. Even the gentle warp seen in the outer neutral hydrogen may be a response to tides that acted through the halo rather than directly through the stellar disk. Because the halo extends so far, encounters with the triangulum spiral or with massive dwarfs can torque the outer layers without immediately unsettling the inner parts. On the smaller scales, questions remain about the number and nature of subhalos inside Andromeda's larger halo. Cold dark matter models predict many small clumps of dark matter that may or may not host visible galaxies. Some may be entirely dark detectable, only through their tug on streams or their subtle lensing of background light. Gaps and wiggles in streams have been interpreted as the footprints of such invisible clumps. If confirmed in larger samples, these features would sketch a map of the halo's substructure and test ideas about the particle nature of the dark matter itself. The ratio of mass to light rises with radius, and that rise has consequences for how the galaxy evolves. Gas that falls in from the intergalactic medium meets the hot atmosphere and may be held at high temperature unless it can cool along filaments or in the wakes of satellites. Where cooling succeeds, fresh fuel reaches the disk and star formation continues. Where it fails, the outer disk may starve while the halo slowly gains more hot gas. Feedback from supernovae and from the central mass can heat and stir the atmosphere, altering this balance. In Andromeda, the present pace of star formation is modest, and the halo likely acts as both reservoir and regulator. None of these inferences show the dark matter directly. They trace its presence through consequence. They point to a component that does not feel light, that does not collide with itself in the way gas does yet, that gathers into halos under gravity, and provides the scaffold on which luminous galaxies are built. The Andromeda halo is one such scaffold, and its properties echo those of halos inferred across the sky. Its study benefits from proximity, because individual streams and satellites can be resolved, because rotation can be measured far out, and because old stars in the halo can be counted one by one in deep images. Even so, the true nature of the dark matter remains an open question. Proposed particles span a wide range of masses and interaction strengths, and experiments on Earth and in space pursue signs that would identify the dark matter directly. Until such signs appear, the halo stands as a measured necessity and a mystery in the same breath. Its existence sets the frame within which Andromeda's visible parts move and change. Its reach sets the scale for the coming encounter with the Milky Way. Its shape and substructure control how streams dissolve and how satellites fade. The approach inward must therefore keep the halo in view even when the eye falls upon the bright disk, for the invisible mass dictates the stage upon which the visible plays. From the halo the path leads to the fossil ribbons that wind through it, the streams and shells that record how Andromeda fed itself over time, and to the companions whose paths thread the outer darkness before they come near the light. Filaments of starlight unwind through the outer darkness like pale rivers, each one a record of a smaller galaxy stretched by tides and folded back upon itself until its pieces trace arcs and loops around Andromeda. The finest exposures reveal these structures as faint over-densities against a sea of old halo stars, their curves so broad that only a patient mosaic can display them whole. The most prominent ribbon drops from the southern quadrant and sweeps toward the inner regions, before fading beneath the brighter disk, a structure so extended that its beginning and end overlap on the sky without meeting in space. Its stars are older on average than those in the spiral arms, and hold more heavy elements than the most primitive dwarfs, a hint that the fallen progenitor was not a feeble spheroidal, but a modest galaxy with its own history of enrichment. Along the stream clumps appear where the original galaxy's central parts resisted shredding a little longer, and those knots now drift as coherent fragments, each with its own slight spread, in speeds that preserves memory of the initial orbit. North and east of the centre, great shelves of light rise like tidal terraces, the visible marks of where debris slowed and piled at the far points of its oscillation. Such shelves form when stars torn from an intruder move on elongated paths inside the host halo. At the turn of those paths where inward motion halts before falling back, density increases and a broad arc brightens. This is phase wrapping a simple idea played out across a grand stage. Pull a galaxy apart, let its stars orbit in a common potential, and the distribution of those stars thickens at certain radii as their phases line up. On the western side, a corresponding shelf catches the eye lower in surface brightness, yet linked by models that follow a single accretion event through the host halo. Together, the southern ribbon and the paired shelves outline a long meal in progress, rather than a set of unrelated leftovers. Several globular clusters ride within or near these features, and their motions match the general flow. Their presence offers two clues. First, the progenitor likely carried its own cluster system, and some of those clusters now mark the stream like buoys. Second, clusters along the debris let velocities be measured even where individual stream stars are too faint for precise spectra, and those velocities define the pull of the halo at large radii. The resulting fits prefer a halo whose density decreases smoothly with distance and may be mildly flattened, because the precession of the stream's orbit and the spacing between shelves both depend on the shape of the gravitational field. The progenitor itself becomes a puzzle with several candidate solutions. One compact elliptical companion just off the bright disk shows signs of tidal stress, and a stellar population that resembles parts of the stream, leading to the idea that it could be the remnant core of the intruder whose outer layers now draw the southern curve. Another bright dwarf slightly farther out carries shells and distortions that speak of its own interaction with Andromeda, and some have proposed that it, rather than the compact neighbour, seeded the main debris. A third view argues that the true progenitor was once larger than either surviving dwarf, perhaps a small spiral that lost most of its mass during a deep plunge, leaving behind a compact nucleus that bears only a partial resemblance to the stream's chemistry. Each possibility draws support from a different emphasis in the data metallicity gradients along the debris thickness of the stream distance, offsets between parts, and the exact positions of the shelves. None has closed the case which keeps the scene alive with open work. Other streams lace the halo like fine threads. Shorter arcs cross near the periphery, some thicker and more diffuse, others narrow and sharp. a set of low brightness loops encircles the outer regions, and could be the remains of still earlier feasts, their stars spread around nearly complete orbits by the slow winding of time. Several of these features align with a thin plane that also hosts a notable fraction of Andromeda's dwarf companions. If that alignment is more than chance, it suggests that material and small galaxies fell in along a preferred direction set by the larger scale filament that feeds the halo. The idea is simple matter does not arrive from all directions equally, and past infall can leave a long memory in the geometry of both streams and satellites. The streams carry more than shape. Their stars tell of origins through their mix of elements. Old metal poor stars point to primitive dwarfs. Intermediate abundances and a tale of younger ages point to more substantial progenitors that formed stars until near the time they were captured. Measurements along the southern ribbon reveal a composition higher than that of the faintest dwarfs, now near Andromeda, again favouring a progenitor of some size. Where star counts grow thickest, a broader spread in metallicity appears consistent with the idea that the central parts of the intruder were more enriched, and that those parts dwell near the densest sections of the stream. Kinematics add another layer. Line-of-sight speeds climb and fall along the curves in a way that, when combined with distances, pinpoints where the debris lies in 3 dimensions. Parts that look contiguous on the sky may in fact be far in front or behind the main body, and this depth helps to connect shells with the ribbon, and to trace how the orbit has precessed between successive wraps. The models that best match these relations place the first strong passage several billion years ago, with subsequent loops and shelves formed as the stars from the intruder continued to oscillate inside the halo. Because the halo itself may be slightly flattened, the plane of the orbit shifts over time, and the stream appears to change orientation from one wrap to the next. Substructure within the halo leaves whispers on the streams. Small clumps of dark matter, even if entirely starless, can tug at a ribbon as it passes, heating it locally and knocking out narrow gaps. Several such underdense spots have been reported along the southern feature, though confidence depends on how well the background and foreground have been subtracted. If confirmed in larger numbers and in multiple streams, these gaps would help weigh the population of small dark matter clumps and test ideas about the dark matter particle itself, because different particle properties predict different numbers of clumps at small masses. The outer disk does not sit idle in the presence of these encounters. Gentle warps and lopsided light may carry the echo of past tides raised by a massive intruder. A ring of star formation at a certain radius, nearly circular, yet slightly offset from the centre, could be the lingering wake of a passage that compressed gas along a wave that now coasts through the disk. The timing of such structures, inferred from the ages of the stars within them, can be compared with the orbital history of the mainstream, to see whether one event might be responsible for both halo debris and inner ripples. In this way, the streams become a bridge between the unseen halo and the bright interior. The deepest images extend the census outward and downward in surface brightness, finding yet fainter curls and wisps that broaden the record of accretion. Each newly traced feature adds a constraint on the halo's shape, and on the rate at which Andromeda consumed its neighbours. Together they paint a picture in which the halo is not a smooth bath of old stars, but a patchwork of overlapping remnants, some only now mixing into the background. Where 2 streams cross, the combined density lifts above the detection floor, and those crossings can masquerade as distinct structures. Careful mapping of distances resolves such overlaps and preserves the true count of past events. The streams and shells also set a standard for interpretation beyond Andromeda. In more distant galaxies, the same physics must play out, but the debris sits beyond the reach of star counts. Instead, the experience gained here trains the eye to look for global signs, asymmetric halos off-center envelopes and faint plumes that echo the brighter patterns around Andromeda. The local lesson then becomes a general method, and the nearby case remains a benchmark against which more distant guesses can be checked. Through all of this, the mood remains quiet rather than dramatic. These structures do not blaze, they whisper. Their power lies in patience and in the way small differences in density, speed and composition accumulate into a long memory. The southern ribbon will continue to wind, the shells will slowly fade as the stars disperse, and the halo will become more mixed. Yet for now the fossil rivers remain legible. They say that Andromeda grows by taking in the small, and by stirring the result through the depths of an extended controlling halo. They say that the path inward must pass next through the company that still orbits whole, the satellite swarm whose alignments and odd planes invite further questions about coherence within a system where randomness would seem the simpler outcome. Around Andromeda drifts a company of small galaxies, a many-voiced chorus, whose motions, shapes and star histories reveal how a giant spiral governs and grows. Closest to the bright disk hangs a tiny compact elliptical, dense and smooth, with stars packed so tightly that it looks like a bright drop clipped against the dust lanes. Slightly farther out, a larger dwarf elliptical shows a soft oval with hints of faint shells as though tides have folded and refolded its light. Beyond these two, a retinue of low-mass companions extends through the halo, some irregular and gas-rich, with traces of recent star birth, many spheroidal and gas-poor with older populations and quiet colours. Each member moves through the deep potential well that the dark halo provides, and together their positions and speeds sketch the form of that well in 3 dimensions. The census of this swarm grows through deep, wide surveys that push to the limit of surface brightness, revealing that many companions hide not in compact knots, but in diffuse ghosts whose light is so spread that it barely rises above the background. Those extremely faint dwarfs hold only a few thousand to a few million stars, yet their motions imply masses much larger than their light would suggest, a signal that dark matter holds them together. Some show ragged edges and hints of tails, signs that tides from Andromeda or from past passages near other satellites are loosening their grip and beginning to unspool them into the streams traced in the outer halo. A pattern appears in the spatial distribution of many companions. A thin plane slants across the halo, within which a notable fraction of dwarfs sit almost like beads on a tilted string. Line of sight speeds along this sheet suggest a common sense of rotation for several members, as if the plane turns slowly around Andromeda. The thinness of the arrangement, the apparent coherence of motion, and the number of satellites involved pose a challenge to a picture in which small galaxies arrive from random directions and settle into orbits with no preferred alignment. One family of explanations invokes the larger scale environment. Matter flows along filaments on its way into halos, and groups of small galaxies may fall in together along a shared path. If so, a thin structure could persist for a long time, especially if the halo is only mildly flattened. Another idea points to tidal debris from a single massive accretion, with bound fragments moving along similar orbits. A third view stresses the role of observational bias, noting that thinness and coherence can be overstated if only the brighter satellites are counted and if distances carry systematic offsets. The present state keeps the puzzle alive. The structure is striking, and yet its origin remains unsettled. Kinematics refine the picture. For many dwarfs, line-of-sight velocities are measured from the narrow absorption lines of their stellar populations. A few brighter companions allow internal dispersions to be resolved, letting mass be estimated from the random speeds of their stars. Where a dwarf shows a cold, coherent velocity field, a past disk may be inferred. Where it shows hot isotropic dispersions, a spheroid shaped by long tides, and gas loss is more likely. Proper motions across the sky are difficult at these distances, but for a handful of close or bright satellites, long baselines with space-based astrometry have begun to yield tiny transverse components. Combined with the line-of-sight speeds and distances, those components determine orbits more directly and test whether the thin plane truly rotates as a set. The results so far hint at partial coherence, not a perfect ring, and suggest that the structure could be a long-lived mode rather than a transient accident. Star formation histories vary with environment. Irregular dwarfs at larger radii often retain cold gas and show scattered pockets of young blue stars, proof that they are still forming suns. Spheroidal dwarfs near Andromeda are largely quenched, their stars older and their colours redder. Two processes can explain this difference. Ram pressure from the hot, thin atmosphere that fills the inner halo can strip gas from a small galaxy that plunges through it at several hundreds of kilometers per second, removing the raw material for future stars. Tidal stirring during repeated close passes can heat a dwarf's disk and drive gas outward, where the same hot medium can more easily carry it away. Both leave survivors that are puffy gas poor and gradually fading, exactly the type seen clustered toward the center. The compact elliptical companion near the disk stands out in both structure and origin. Its unusually high central density and small size suggest that it is the stripped core of a larger system. In one reading, a small spiral or bright dwarf once fell close to Andromeda, lost its outer stars and gas to tides, and left behind a concentrated nucleus that now orbits in plain view. Its counterpart, the somewhat larger dwarf elliptical, bears shells and gradients that may record a related though less extreme history. These two bright companions then become living links between the streams that lace the halo and the survivors that still move whole. Their globular clusters and planetary nebulae provide additional traces for distance and motion, tying their paths to the wider field. The swarm contains pairs and small groups of satellites whose mutual pulls complicate their tracks. A pair to the northwest shows evidence that one has stirred the other, with differences in metallicity and shape that speak to separate origins followed by a shared present. Such substructure within the retinue hints that parts of the swarm arrived as bound associations, rather than as solitary bodies, again consistent with infall along a filament or within a group. On the larger scales, the counts of visible dwarfs around Andromeda face a long-standing tension, with simple early theories that predicted many more small halos than luminous satellites. Better surveys have since found fainter and fainter systems narrowing the gap, and physics that links star formation to halo mass explains how many small halos might host few or no stars. In this view, the most fragile subhalos never gathered or retained enough cool gas to light up, while the ones we see survived long enough and large enough to cross the threshold. The result is a swarm that is numerous but not overwhelmingly so, with a steep rise toward low luminosities and a broad span of sizes and surface brightnesses. The distribution in distance from Andromeda reveals that many satellites reside within a few 100,000 light-years of the center, with a tail that extends outward toward the reach, where the dark halo fades into the general matter of the local group. Some dwarfs in this outer tail may feel nearly as much pull from the Milky Way as from Andromeda, and their long-term allegiance could change over cosmic time, as paths carry them across the saddle between the two giants. The approach speed of Andromeda itself complicates matters further, since shrinking separation changes the gravitational field in which the satellites move and may alter the stability of thin structures. The satellite swarm also touches the story of the Triangulum spiral. If Triangulum is bound to Andromeda on a long inclined orbit, its tides could have stirred the outer gas and contributed to the gentle warp in the disk. It could also have dragged along small companions that now join the swarm. If it only flies by on a wide path, the imprint would be different, a one-time flex rather than a long ongoing influence. Distinguishing these cases matters for timing the events that wrote rings, shelves, and asymmetric star-forming regions within Andromeda. Through all of this, the mood remains steady. These are not dramatic fireworks, but quiet processes playing out over long spans. Tiny differences in energy at one passage can set a dwarf on a course that after many orbits returns it to a different depth and phase. Gentle stripping can puff a disk into a spheroid and then into a stream. A plane of satellites can hold for billions of years if fed with new members along the same direction, and if the host halo's shape is friendly to such coherence. The satellite swarm is therefore more than a catalogue. It is a dynamical chemical and historical record that complements the streams and frames the disk. To move inward from here is to carry that record along, for the signatures of past tides among satellites will appear again as warps, rings, and lopsided light within the bright starry body of Andromeda itself. The bright body of Andromeda does not lie flat like a perfect coin. It breathes and bends, and the bend reveals how tides and long memory shape a disk that otherwise looks composed. Neutral hydrogen. The cool diffuse gas that outlines the widest lanes tilts gently upward on one side and downward on the other, so that the outermost orbits climb out of the main plane like the lip of a plate left too long in warm water. This warp grows stronger with distance from the centre, small near the bright inner arms and more pronounced across the faint outskirts, a sign that the deep pull of the halo and the low density of the outer disk allow even slight torques to sculpt the form. The sources of those torques leave several fingerprints. Close bright companions have likely passed near enough to raise tides in the gas layer, drawing it out of alignment, and then letting the pull of the whole halo bring it back slowly toward the midplane. The long orbit of the Triangulum spiral, if bound, can add a slow twist as it circles, while the debris of past accretions adds uneven mass that the gas must settle around. The disk answers these influences with a mixture of compliance and resilience, bending where it is light, holding shape where gravity from stars is strong, and passing the imposed curve inward as a gentle undulation. Along the disk a different asymmetry appears, not in tilt but in brightness and structure. One side of the outer arms sparkles with more frequent knots of star formation than the opposite side, and the lane of dust that cuts the near side of the inner disk seems sharper and more continuous than its counterpart. These gradients hint that the inflow of gas is not perfectly even. Where the warp draws the gas slightly out of the main plane compression, where it returns to the midplane can ignite larger patches of starbirth. The result is not a simple bar of light, but a ring that stands out at a radius of several tens of thousands of light-years, bright in emission from hydrogen, and crowded with luminous young clusters. The ring is nearly circular, yet it sits slightly off-centre, and its inner and outer edges ripple with subtle spirals. Such a pattern can arise when a past encounter drives a wave into the gas that then travels around the disk. As the wave passes, gas piles up and collapses, and the newborn stars mark where the crest has moved. Ages of clusters along the ring can reveal the direction and speed of that travel, and some studies suggest that the wave has passed through different sectors at different times, which fits a picture in which a single passage long ago continues to echo as the wake slides around. The inner disk carries its own quiet imbalance. Light profiles measured along the major axis do not match exactly on the two sides of the core. The difference is small and smooth rather than jagged. an offset that could be caused by an elongated mass at the centre or by an oval distortion in the distribution of old stars. Gas motions in the same region show slight non-circular components, as if material is not only circling but also drifting slowly inward along curved paths. Where these drifts meet the ring, gas piles grow, and star formation strengthens again, reinforcing the asymmetry. Spiral structure across the disk is also uneven. The two main arms are not identical twins. One is broader and more continuous across a long arc, while the other breaks into segments, with patches of more vigorous starbirth separated by quieter gaps. This pattern may reflect a difference in how the arms are supported. In one case, the density wave may be stronger and more long-lived in the other. The arm may be a transient pattern, reinforced by local gravitational instabilities in the gas. The contrast between arms is clearest where the ring crosses them, and the intersection produces regions studded with young clusters and glowing gas clouds whose brightness fades into the interarm zones. Even the thickness of the disk changes with radius. Near the centre, a thin layer of young stars rotates quickly and lies close to the midplane, while a thicker older component wraps around it, with slower rotation and larger vertical spread. Farther out, flares appear with the scale height of the disk increasing as the density falls and as tidal heating from satellites lifts stars into slightly higher orbits above and below the plane. The vertical breathing taught by minor encounters thus alters the apparent edge, making the frontier of the disk a soft fade rather than a hard cut-off. Radial motions add another level of detail. Gas does not only circle, it also drifts inward by small amounts under the combined influence of gravitational torques and pressure gradients. Where the drift is stronger on one side, a lopsided pattern in gas density develops that can last for long spans. This lopsidedness is seen in the way the neutral hydrogen distribution extends farther on one side of Andromeda than on the other, and in the slight displacement of the dynamical centre, inferred from gas motions compared to the photometric centre, traced by starlight. The mismatch is small, but it speaks to a disk that has not yet fully settled after past pulls. Starlight maps also show fine ripples in the outskirts that resemble the low amplitude waves left on a lake after a passing boat. These ripples can come from the gentle flex of the disk as the halo relaxes from a past accretion, or from the slow precession of the warp under the pull of a mildly flattened mass distribution. Because stars remember vertical kicks for a long time, such waves can persist, offering a long baseline through which the disk's history can be read. Globular clusters embedded in the disk and the inner halo help to time these events. Clusters with orbits close to the plane, and with ages that match the timescale inferred for the star-forming ring, suggest that some of the inner heating occurred within the last few billion years, consistent with the leading candidates among the companions for a disturbing passage. Meanwhile, clusters in more inclined orbits with older ages point to ancient events that predate the present set of asymmetries. Together, the clusters become test masses that sample different layers of Andromeda's memory. The rotation curve provides a firm, nearly flat spine through this complexity. Despite warps, rings, and lopsidedness, the speed of gas along the major axis remains high from the inner few thousand light-years out to well beyond the bright arms. Small wiggles sit on top of the flat run linked to arm passages and to streaming motions. Those wiggles are modest, which implies that the underlying gravitational field is smooth and dominated by the halo. The disk rides within that field like a flexible sheet on a broad frame, crumpling slightly, where forces change yet held overall to a near constant spin by mass that lies far beyond the luminous core. Dust deepens the visible contrasts and paradoxically clarifies the underlying flow. On the near side of the disk, dust lanes cut across the bulge in crisp strokes, making the tilt clear and helping to determine which side lies closer by tracing where dust obscures light most strongly. On the far side, the lanes are muted and the brightness profile falls more smoothly. Infrared maps pierce the obscuration and show where cold dust and gas pile into the ring, and arms matching the asymmetric layout seen in emission from excited hydrogen. By comparing patterns across wavelengths, observers separate shape from shadow and confirm that the asymmetries are real structures rather than tricks of extinction. The overall impression is of a living disk that responds to its environment with subtle but measurable departures from symmetry. It warps where the outer halo invites a twist. It brightens in a ring where a past wave continues to circle. It carries slightly different arm strengths on its two sides, and it drifts inward more on one sector than the other. None of these features by itself erases the identity of Andromeda as a grand design spiral. Together they show how even a mature galaxy holds the imprint of encounters and of ongoing exchange with its surroundings. The approach inward therefore continues with an eye sharpened by these patterns, for the next structures to enter view the spiral arms themselves, and the gas that threads them are both shaped by, and in turn help to sustain the asymmetries that give the disk its quiet, distinctive character. Across the bright body of Andromeda, the spiral arms lean outward like slow waves frozen in rotation, yet the stillness is only an appearance produced by immense scale. Gas dust and stars drift through the arms, slowed and guided by a pattern that turns as a whole with its own patient speed. The idea of a density wave explains this quiet order. In such a wave, the arm is not a rigid structure, but a crest in the gravitational field where material piles briefly before flowing on. Stars of many ages cross the crest nearly unhindered, but gas being cold and compressible responds more strongly. As the gas enters a region of higher density, it experiences a small but persistent squeeze that raises pressure, triggers shocks and forces clouds to contract. In the wake of this compression, new stars ignite, and a sequence appears along the arm's length and width. First a narrow dust lane that marks the shock front, then bright knots of ionized hydrogen, where the hottest young stars flood their surroundings with energy, then slightly older blue clusters, then a wash of intermediate age light that blends into the interarm regions. This ordering is clearest where the arm is strong and the flow is orderly, and it softens where the arm is patchy, or where the gas has already been stirred by previous passages. Andromeda displays both modes within one disk. One arm broad and gently curving carries long stretches where the dust lane, the bright gas, and the young clusters line up with textbook clarity. The partner arm shows more broken segments with islands of star formation, separated by quieter gaps, and with dust lanes that twist and reconnect. Streaming motions measured in the gas confirm that material slows as it approaches the crest and speeds up as it leaves, adding a few tens of kilometers per second to the local flow on top of the near constant rotation set by the halo. Those streaming speeds, while small compared with the overall spin of several hundreds of kilometers per second, are exactly the scale needed to compress clouds without tearing them apart. The pitch angle of the arms, the measure of how tightly they wind, changes with radius opening slightly in the outskirts, where the disk is more easily flexed by the halo and by past tides. Near the radius of the star-forming ring, the arms and the ring interact with the ring's nearly circular wave, modulating the strength of the spiral pattern. Where the ring crosses an arm, gas piles higher, and star formation gains an extra push, producing crowding of clusters and glowing regions that age gradients then smear downstream. Farther inward, the spiral pattern weakens and gives way to oval distortions in the distribution of old stars. These distortions can send gas along curved paths toward the center, feeding inner rings and faint dust spirals that hint at slow inflow. In such regions, the density wave becomes less of a grand design and more of a local organizer that cooperates with the oval. The pattern speed of the wave, its turn rate as a whole, sets special radii, where the relation between the orbital period of stars and the wave becomes resonant. At the corrotation radius, material circles the center at the same rate as the pattern, and therefore lingers near the crest, for longer broadening the arm and softening the contrast. Inside the inner Lindblad resonance, the wave can weaken or split, and outside the outer Lindblad resonance, the arm can fade into transient spurs. Observationally, dust lanes and young star fields in Andromeda show features consistent with such resonances, a change in arm contrast near a mid-disk radius that could mark corrotation and inner zone where dust spirals, rather than forms a clear arm pair and outer segments that taper and break into feather-like branches that point backward with respect to the direction of rotation. Spiral arms are not only sites of birth but also of feedback. The youngest and most massive stars live short lives and return energy to their surroundings through winds and through their deaths. This energy stirs the gas calves, bubbles and shells that glimmer in ionized hydrogen and seeds turbulence that can both disrupt clouds and prepare new ones by compressing gas along expanding fronts. In Andromeda, the arm segments with the brightest young clusters often sit beside evacuated cavities, and the size and frequency of such cavities vary, with radius being larger and more common, where gas surface density is higher and gravitational pull is slightly weaker. The regularity of the arm's star formation rhythm is therefore tempered by the self-regulation of the gas, which does not let any region continue forming stars at a fixed high rate for long. Magnetic fields thread the disk and align roughly with spiral structure, adding gentle tension that can channel gas flows along the arms and help shape the narrowness of the dust lanes. Polarized radio maps show that the field is smoother in the interarm regions and more tangled within the arms, a signature that turbulence grows where stars are born, and that the orderly field lines are stretched where gas shears between arm and interarm. The field strength is modest compared with gravity, yet it matters for how clouds assemble and for the rate at which dense cores form within them. The contrast between arm and interarm is not absolute. Many clusters begin just downstream from the arm crest, and drift farther as they age, and some stars form in spurs and feathers that branch from the main pattern, where shear and self-gravity cooperate. These secondary features can extend for thousands of light years and create bridges between arms seeding patchy star formation, away from the main crests. In Andromeda, the side of the disk that shows stronger recent star birth hosts, more of these feathers, consistent with the idea that the overall lopsided gas distribution discussed earlier supports stronger shear features there. The lifetime of a spiral pattern is a question that remains open in detail. A steady density wave can in principle persist for many rotations if maintained by the self-consistent response of the disk and by mild driving from companions. Transient arms can also arise naturally as instabilities grow and wind up, then fade and are replaced by new ones. The mixture in Andromeda suggests a hybrid picture, a long-lived underlying two-armed mode that sets the broad layout upon which transient segments and local instabilities ride, thickening one arm and fragmenting the other, in response to recent history and to the current gas supply. The connection to the satellite swarm and to the warp is therefore indirect but persistent. A past tidal nudge can change the phase and strength of the wave. A continuing slow torque can keep one sector supplied with more gas and therefore richer in young stars. Embedded within the arms are rich associations of hot, massive blue stars whose light dominates the ultraviolet view, and whose ages can be read from their colours and from the absence or presence of very massive members. By lining up these ages along a cut across an arm, one can time the passage of the density crest and estimate the pattern speed. In several sectors of Andromeda, such age gradients point to a pattern period measured in hundreds of millions of years, a timescale that fits the measured streaming speeds and the nearly flat rotation curve. Along the way, cold molecular clouds appear upstream of the youngest clusters, then peak near the shock lane, then wane as feedback clears the immediate surroundings. This choreography repeats at different radii, with variations introduced by the ring the warp and the mild oval at the centre. The arm interiors also hold older populations that did not form there but crossed from elsewhere, proof that arms gather and shape stellar orbits without owning the stars forever. Because stars spend more time near the apices of their small epicyclic motions, they can appear to crowd at certain phases relative to the wave, even without a recent birth there. Disentangling this crowding from genuine young concentrations is part of the careful work of mapping star formation histories. In the sum of these layers, Andromeda's spiral arms are not ornaments but engines that modulate the conversion of gas into stars and that transmit the memory of the larger environment into the daily weather of the disk. They channel inflow from the ring into clusters, they export turbulence into interarm space, they host resonances that shape the geography of birth, and they slowly move material inward as torques act over time. The next inward step follows the path of the dust lanes into the colder reservoirs themselves, into the molecular clouds, and the dark belts where stars are prepared in silence before they flare into view along the arms. Dust draws the first clear lines across Andromeda's face, not as an absence, but as a substance that shapes like chemistry, and the pace of birth inside the disk. In the near side of the spiral, dark lanes cut the bulge in firm strokes, each lane a crowded belt of tiny grains mixed through cold gas and nudged into filaments by gravity shear and magnetic tension. These grains are not mere ash. They are factories and shields. They gather ice mantles, they catalyze the assembly of simple molecules on their surfaces, and they block the harsh blue and ultraviolet light that would otherwise tear fragile bonds apart. Behind this shelter, hydrogen pairs into molecules, and carbon joins oxygen, and the gas cools into the low tens of degrees above absolute zero, a state where pressure drops enough that self-gravity can begin to collect matter into dense clumps. The lanes look continuous from afar, but high-resolution views show that they are braided from many sublanes and knots, with gaps where pressure and feedback have cleared cavities, and with bridges where turbulence has spun filaments into crossing threads. The coldest reservoirs sit inside these braids as giant clouds spanning tens to hundreds of light-years each cloud, a landscape of denser cores wrapped in a more diffuse envelope. Lines from molecules reveal the distribution of this cold gas, especially the emission from carbon monoxide that glows softly at radio wavelengths, and traces where molecular hydrogen would otherwise be invisible. In Andromeda, the carbon monoxide glow outlines the ring, and the stronger spiral segments concentrates along the sharper dust lanes on the near side and thins across the interarm spaces. Within the ring, knots of emission match the large complexes that later shine in ionized hydrogen, confirming that cold gas is the raw material that the arms and wave rings then compress into clusters. The mass locked in these clouds spans a wide range from small clumps with only thousands of solar masses up to giants that weigh millions of solar masses. Most clouds live only a few tens of millions of years before either collapsing into stars or being torn apart by the very stars they form. In that brief life, turbulence plays the role of both support and sculptor. Colliding flows, spiral shocks, and the push from previous generations of stars stir the gas into a fractal pattern with dense pockets nested inside looser shells. Magnetic fields thread this pattern and slow the rate at which gravity can fold material inward, guiding flows along field lines so that filaments become the default shape of collapse. Where several filaments meet, knots form and new stars begin. The threshold for this change from cold reservoir to active nursery depends on pressure, metallicity and radiation. In Andromeda, a gentle radial gradient in heavy element abundance and in dust to gas ratio makes clouds in the outer disk slightly less efficient at gathering mass than those nearer the centre, matching the observation that luminous star-forming regions crowd more densely in the inner part of the ring and in the stronger arm. Dust sets the light's tone as well as the gas's chemistry. It dims and reddens the starlight behind it in a way that depends on grain sizes and compositions. By comparing the dimming across many wavelengths, observers infer that Andromeda's grains resemble those in the Milky Way, but carry subtle differences that track the metallicity gradient and the relative contributions of ancient and recent star formation. In the far infrared and in the sub-millimeter bands, the grains themselves glow with the heat they have absorbed. Maps in these bands reveal cold dust lying just inside the main arm shocks and reaching peak brightness around the ring, where the balance between gentle heating by older stars and sharper heating by nearby young clusters drives a patchwork of temperatures. Interspersed with the cold components are aromatic molecules that respond to ultraviolet light with broad emission features. These signals outline the skin of each cold region where starlight slips in and creates a chemical frontier between fully shielded interiors and the bright outer layers. The interplay between shielding and erosion sets the width of the dust lanes. On the illuminated side, hydrogen returns to atoms and carbon lifts into ionized states, while deeper inside the gas remains molecular and cool. As clusters ignite along an arm, their winds and radiation inflate cavities and punch holes through which light escapes, sculpting the lanes into arcs and bays. Over a few million years, the combined push of winds and supernovae can shred the parent cloud and scatter dust into the surrounding medium, where it will be gathered again by the next passing wave. The flow is circular in more ways than one. The density wave sets up the shock that collects dust and gas. The dust enables molecules, and cooling the molecules allow collapse into stars, and the new stars return energy that resets the conditions for the next cycle. This cycle does not run at the same pace everywhere. In sectors where the warp brings gas back toward the midplane, compression strengthens, and lanes thicken, increasing the fraction of mass in cold clouds. In sectors where the gas layer lies slightly above or below the midplane, or where previous feedback has evacuated large volumes, the lanes thin and star formation falters. This unevenness feeds the lopsided pattern noted earlier and helps explain why one side of the disk shows brighter chains of ionized hydrogen regions, while the opposite side looks more quiescent. Gravity and pressure are joined by shear in setting cloud fates. As gas enters, an arm differential rotation tugs on filaments, stretching them parallel to the arm's length. Once past the crest, the same shear can tear clouds into spurs that angle backward toward the trailing side of the wave. These spurs act as seeds for interarm star formation, and as pathways along which dust is redistributed. Along many such spurs in Andromeda, faint streaks of dust connect the bright arm to the quieter space between, giving the disk a woven appearance when seen in combined starlight and dust light. The coldest cores inside the larger clouds are the places where the dust becomes the most effective shield. Temperatures drop to only a few tens of degrees above absolute zero thermal speeds fall, and heavy molecules that would not survive in a more exposed environment appear in weak emission. In these cores, grains grow mantles of water carbon dioxide, and more complex species turning the dust into carriers of chemistry between cycles of collapse and dispersal. When a core collapses, some of these ices heat, evaporate, and enrich the newborn surroundings, beginning the slow build of elements and compounds that over many generations will seed planets and life in distant futures. The scale of the ring in Andromeda makes it a laboratory for how dust and cold gas respond to a mild, long-lived wave. Ages of clusters around the ring show a gentle gradient consistent with a pattern that rotates more slowly than the gas, while the dust temperature pattern shows where recent energy input has been stronger. The deepest observations show knots along the ring that look like beads on a string suggestive of gravitational fragmentation, along a ridge pushed inward by the wave. Each bead contains several cold clouds, and each cloud hosts multiple dense cores, setting up a hierarchy of structure that stretches from hundreds of light years down to fractions of a light year. Though the halo controls the rotation curve and the outer dynamics, the day-to-day weather of the disk is written by dust and cold gas, and that weather decides where and when bright clusters will appear. Subtle variations in dust-to-gas ratio with radius, combined with differences in pressure and shear, create a map of likely future birthplaces that can be read in the cold emission. The link between dust lanes and future ionized hydrogen regions is therefore statistical but strong. The darkest lanes are the most likely places to see the next wave of young light, though any given knot may fail if feedback arrives too early or if shear proves too strong. This quiet complexity does not erase the calm of the scene when viewed whole. The lane's clouds and rings form a slow heartbeat. Beneath the flat spin of the disk, a measured rhythm that turns raw gas into stars and then pauses as the medium recovers. From this level, the path draws inward again away from the coldest reservoirs and toward the places where newborn clusters declare themselves, where ionized hydrogen glows in pink arcs, and where the brightest association in the southwest of the disk offers a clear stage on which to watch youth assembled by dust and released by the passing wave. Youth announces itself along Andromeda's arms with a soft glow that gathers into knots, arcs, and sprawling complexes where cold gas has been compressed into clusters of newborn stars. Among these, a vast association in the southwestern sector stands out as a broad, luminous pasture of hot blue giants, sprinkled across a field of fainter companions. It is not a single cluster, but a landscape of many groups at slightly different ages, each one tracing a recent crest of the spiral pattern and the ring's passage. The brightest members pour out hard light that strips electrons from nearby hydrogen, and the resulting ionized hydrogen shells form pink arcs and bubbles that mark where radiation and winds push against the surrounding medium. The geometry is three-dimensional, yet on the sky it appears as lace with cavities where earlier generations have cleared paths, and with bright rims where pressure now piles gas into narrow ridges, ages ladder outward from the sharp dust lane on the upstream side. Immediately behind the shock line lie compact knots whose stars are only a few million years old, still wrapped in half-dispersed cocoons. A little farther downstream sit looser groups whose most massive members have already begun to sculpt wide bubbles. Their light has softened slightly, and their winds have swept dust into thin filaments that curve around the cleared interiors. Farther still, the clusters are older by several tens of millions of years. Blue light, less fierce red and yellow stars beginning to contribute to the blend. This gradient is not perfectly smooth because turbulence, magnetic tension, and local self-gravity seed multiple starts along the lane. Even so, a coherent pattern holds the densest cold gas, the youngest clusters, and the brightest ionized hydrogen arcs align in a sequence that mirrors the flow through the arm, Within the Southwestern Association, carbon monoxide maps show giant molecular clouds arrayed like stepping stones. Each cloud spans tens to hundreds of light years and carries a nested hierarchy of dense cores. Where several filaments converge, massive clusters form, and feedback from those clusters quickly changes the scene. Winds from hot stars carve channels that vent outward, allowing light to escape and illuminate distant dust in reflection. Supernovae arrive on a timetable measured in only a few million years, punching holes in the shells and stirring low-density interiors into a turbulent froth. This energy both hinders and helps the next round of birth. It can shred nearby cores before they collapse, yet it can also drive converging flows along expanding boundaries where gas cools and gathers again. In the association, bright arcs often trace the borders between older cavities and fresh cold ridges, a sign that sequential triggering proceeds along curved fronts that drift with the disk's shear. Star formation within such a complex is not perfectly efficient. Only a small fraction of the available gas turns into stars before the rest is blown outward or mixed into the general medium. This inefficiency keeps the overall pace modest and prevents the disk from exhausting its fuel too quickly. Still, for a brief interval, the local rate can spike where the wave and ring overlap, and the southwestern complex seems to sit near such a confluence. The ring's nearly circular wave brings gas inward toward a preferred radius, while the spiral crest focuses compression along an oblique lane. Where these two structures cross, clouds find themselves squeezed from two sides and large associations blossom. The colours of the brightest clusters map their short lives with precision. The most massive blue giants burn for only a few million years before ending as supernovae, leaving behind clusters whose light shifts toward less blue tones even as the total brightness remains high. By fitting the combined light of each group with models that sum the contributions of stars across a range of masses and ages, observers recover star formation histories that reveal bursts timed by the passage of the wave and by local feedback cycles. In the southwestern field, the pattern points to several bursts spaced by intervals of several million years, as though a long ridge fragmented into beads that lit up one after another along the lane. The association is not isolated. Fainter chains of clusters extend into the interarm region as feathers that angle backward with respect to the direction of rotation. These feathers likely began as spurs torn from the main shock by shear, and they act as pathways for star formation to continue at a lower level away from the crest. The presence of these bridges explains why the disk between arms is not entirely quiet, and why age gradients, though clear near the shock, become more mixed farther downstream. Ionized hydrogen regions within the complex come in many sizes. Some are compact spheres around single very hot stars. Others are grand shells, hundreds of light years wide around multiple clusters whose winds and radiation combine. Several show central cavities almost empty of gas, bounded by thin, bright rims where pressure has gathered the remaining material. Along those rims, secondary star formation sometimes appears as tiny knots, just a few million years old, proof that feedback's outward push can also assemble new cores. Filaments linking separate shells reveal that the cavities interact, merging into super bubbles that eventually vent into the higher layers of the disk, feeding a fountain of warm gas that will cool and rain back into the plane at new radii. The chemical signature of the young stars in this sector carries the mark of a disk that has been enriched by many past generations. Abundances of oxygen and other elements heavier than helium decline gently with radius, and the Southwestern Association sits at a point on this gradient where the mix allows dust to be common and cooling to be efficient. The resulting high fraction of molecular gas makes the region fertile, but the same enrichment ensures that radiation from the newest stars couples strongly to the dust, heating it and enhancing emission at far infrared wavelengths. Maps at those wavelengths show the association as a bright patch girdled by cooler filaments, matching the view in ionized hydrogen and in carbon monoxide and tying together light gas and dust into a single portrait. Kinematics measured from the narrow lines of ionized hydrogen reveal streaming speeds on top of the global rotation a few tens of kilometers per second inward, where gas approaches the crest and outward where it departs. Superposed upon these are expansion speeds of shells that reach similar values on smaller scales. These superposed motions complicate the simple picture of circular flow, yet they carry the crucial information about how energy moves through the medium and how gas is redistributed within the arm. Combined with distances for clusters across the face of the complex, the velocities let the three-dimensional structure be inferred. Some bright arcs sit in front of the main dust lane, some behind it, and some thread the plane like tilted bowls, whose nearer lips appear sharper because dust on the near side darkens them more strongly. The southwestern association is mirrored by other bright regions around the ring and along the alternate arm, though few match its scale. Together they form a necklace of youth that pulses around the disk. Ages measured around the ring trace a slow drift, consistent with a pattern that turns more slowly than the gas. In places where a companion's pass tug may have sent an extra wave through the disk, clusters with similar ages appear along a nearly circular arc, reinforcing the idea that a single event can seed a ring that persists for hundreds of millions of years, while new clusters light up at different longitudes. The cumulative effect of these regions on the galaxy's light is substantial. They dominate the ultraviolet and blue bands, add texture to the optical view, and heat dust that glows in the far infrared. Over time, however, their gases return to the reservoir, their brightest stars die, and their clusters dissolve as tidal forces within the disk pull them apart. Many stars then join the general thin disk population, while a fraction scatter into thicker components through resonant interactions and minor heating. Thus, a grand association that seems singular today becomes tomorrow's contribution to the broader stellar populations. The calm tone of the galaxy persists through this turnover because the timescales involved, while short for individual clusters, are long for the pattern as a whole. The southwestern complex therefore serves as a clear and local window into general processes. It shows how a wave sets the stage, how dust and cold gas write the script, how stars step onto that stage and briefly alter the setting, and how the scene resets for the next act. It also anchors the move inward to older components, for beyond the bright associations lie regions where new star birth yields to the steady presence of ancient populations. The light there is smoother and redder, the dynamics more dominated by random motions, and the questions shift from gas and feedback to assembly and memory. The path now leaves the ring and follows the gradual change from young clusters to old clusters, from open associations to globular systems, and from the thin, rapidly rotating sheet to the thicker, more slowly spinning structures that belong to earlier epochs of Andromeda's life. Old light fills the spaces between bright associations with a steadier, redder glow, and within that glow live the records of Andromeda's earliest epochs. Scattered across the halo and into the inner regions are globular clusters, dense and ancient swarms of stars that formed when the galaxy was young and that have persisted through tides, shocks, and the slow drift of orbits. Andromeda hosts several hundred of these clusters, more than the Milky Way, and they span a wide range of sizes, concentrations, and compositions. Many cluster cores are as compact as the most crowded fields in any galaxy, while others are unusually extended with low central densities that blur into the surrounding halo. The ensemble is not uniform. A clear bimodality appears when the iron content of cluster stars is measured: a metal-poor group with few heavy elements, and a metal-rich group whose stars form from gas that had already been enriched by earlier generations. The metal-poor group dominates the far halo and shows kinematics that are largely random, with only a faint trace of net spin, as though many members were accreted from smaller galaxies along a variety of orbits. The metal-rich group crowds the inner regions, where a gentle rotation aligned with the disk suggests an origin tied to early dissipative assembly within the main body. Ages inferred from deep color magnitude diagrams show that almost all of these clusters are ancient, older than 10 billion years, with only slight differences between subgroups. That near-uniform age argues that the key phases of cluster formation occurred early, when gas densities and pressures were high, and when the gravitational potential was still settling. A subset of clusters in the far reaches stand out as especially extended, with half-light radii far larger than those of classical globulars. They occupy the low-density outer halo and often sit on or near stellar streams. Their diffuse structure and their association with debris features hint that they are the surviving nuclear star clusters of small galaxies whose outer stars were stripped, or that they grew in gentler environments within those dwarfs before being set adrift. Their orbits and chemistries make them living markers of the accretion events traced by the streams. Between clusters and field stars lies the broad halo population, whose faint wash emerges in deep exposures as a slowly falling brightness with radius. The star mix changes with distance. In the inner halo, a metal-rich component contributes significantly. Red giant branches appear at colors that imply higher heavy element content, and kinematics show some mild rotation that echoes the inner clusters. Farther out, the metal-poor population takes over. The red giant branch shifts toward bluer colors. Blue horizontal branch stars appear in larger numbers, and the velocity distribution grows more isotropic and hot, consistent with a history of many overlapping orbits rather than a single dominant flow. The overall density of halo stars falls with radius along a steep power law, yet bumps and shoulders appear where streams and shells add their local excesses. The halo, therefore, is not a smooth envelope but a palimpsest of ancient events written with different inks and layered through depth. Certain standard candles allow these old populations to be traced across great distances. RR Lyrae variables, stars that pulsate with periods of less than a day and that are characteristic of ancient metal, poor systems speckle the outer fields and define distances to halo substructures. Their presence confirms the age of the metal-poor component and ties it to the kind of low-mass progenitors that in the Milky Way built much of the outer halo. Red clump stars mark slightly younger, more metal, rich populations in the inner halo, and along the interface with the thickened disk, providing a contrast that helps separate components. Planetary nebulae, though more common, where intermediate age populations are present, still appear in the inner halo and in the outskirts of the bulge, adding to the kinematic map through their bright emission lines. The chemical pattern written in old stars carries a second layer of chronology. The ratio of elements made in quick supernovae to those made more slowly in longer-lived systems reveals how fast the gas was enriched. In the inner halo and thick disk enhancements of the quick elements imply that early star formation was intense and brief, leaving little time for slower channels to add their share. In the outer halo, the ratios drift toward values seen in dwarf galaxies, consistent with prolonged slower star formation before accretion. This contrast suggests a two-phase assembly, an initial rapid build of the central regions from gas that cooled and collapsed early, and a long tail of growth through the capture of smaller systems that deposited stars and clusters into the outskirts. Kinematics agree with this division. The thick disk component rotates more slowly than the thin disk and carries larger random motions above and below the plane. Its stars are older, their chemistry more enhanced in quick elements, and their scale height larger. This component very likely records an early epoch when gas was more turbulent, when the disk was puffy, and when minor mergers heated stellar orbits. The inner halo overlaps this thickened structure and shares some of its chemistry while showing less net rotation and a more spheroidal geometry. The transition from thick disk to inner halo is gradual rather than sudden, which fits the idea of a continuous early build punctuated by heating and by smooth infall. The globular cluster system reflects the same gradation. Metal-rich clusters closer to the center show rotation, lower velocity dispersions, and often flatter, more elliptical shapes aligned with the disk and bulge, suggesting that they formed in the densest gas during the early dissipative phase. Metal-poor clusters at larger radii show little rotation, higher dispersions, and a wide range of structural parameters pointing to multiple progenitors and a long accretion history. Several clusters sit exactly on known streams and share their line of sight speed, strengthening the link between clusters and captured dwarfs. A few clusters even show internal spreads in heavy elements, an unusual sign that they may be the remnants of stripped nuclei rather than true simple populations. The spatial map of clusters and halo stars reveals preferred directions. Overdensities align with the thin plane of satellites and with the grand southern stream, while other overdensities trace arcs that match the shelves discussed earlier. The result is a halo whose geometry is shaped by a handful of significant events, rather than by entirely smooth mixing. Even so, within a few tens of thousands of light-years of the center, the metal-rich halo and thick disk blend into a more symmetric structure where individual streams are difficult to pick out against the high background. There the old light smooths into the rise of the bulge. The ancient populations also govern how the galaxy shines in integrated light. They dominate the near-infrared, set the mass-to-light ratio for much of the disk and bulge, and provide the gravitational bed on which new clusters form and dissolve. Their steady presence explains why the total light changes only slowly even when bright associations flare and fade. Over billions of years, the slow conversion of gas into stars shifts more mass into these older components, and the disk reddens, yet the existing ancient stars keep the overall character stable. In the outskirts, where surface brightness is lowest, the detectability of the halo depends on counting individual red giants. There the star counts have revealed that the halo extends to very large radii farther than once thought, and that the metal-poor population forms a nearly spherical envelope beyond the more flattened inner regions. This extended halo connects naturally to the realm where satellites orbit and where the dark matter halo dominates completely, closing the loop between luminous traces and the invisible scaffold. Seen in this light, the ancient populations of Andromeda are not a background but the backbone. They frame the dynamic youth of the arms, preserve the signatures of early assembly, and carry the memories of captured neighbours. They also foreshadow the nature of the central structure. For toward the core the old light brightens, random motions rise, and the geometry changes from disk to spheroid. There the questions turn from streams and clusters to profiles and shapes, to whether the inner swell hides a bar or a triaxial structure, and to how stars move under the influence of a deep central mass. The path, therefore, enters the bulge next, where ancient populations concentrate, and where the balance between rotation and pressure support sets the form that governs the transition from the wide disk to the crowded heart. The inner light of Andromeda swells into a broad elongated rise that at first glance seems a simple spheroid, yet closer inspection shows structure and motion that refuse a single label. Equal brightness contours twist gently with radius. The inner glow appears faintly box-shaped in the infrared, and brightness profiles along the major and minor axes curve in different ways. These clues point to a layered three-dimensional figure whose longest axis sits at a modest angle within the plane of the disk. Shape speaks first. Compared with perfect ellipses, the inner contours look slightly rectangular, a boxy signature commonly produced when a stellar bar thickens through vertical resonances and, seen at an angle, presents a peanut or box outline. The apparent long axis of this box does not align exactly with the outer disk. A slow twist with radius hints at a figure with three unequal axes rather than a round swell, and straight inner dust lanes meet the bright body in a way that suggests leading edges of an elongated structure. On the near side, a firm dust stroke cuts the bulge with crisp contrast. On the far side, dust softens into curves and arcs. This asymmetric masking is not illusion alone. It reveals shocks and streaming that betray the presence of a bar and the paths along which gas is shepherded by the underlying pattern. Motion adds weight. Spectra taken along several position angles show rotation that remains strong inside the bright swell, while the central rise in random speed is pronounced and extends farther than a thin disk can explain. Maps that combine many pointings reveal zones where rotation is nearly the same at different heights above the plane, a near-cylindrical behavior seen in thickened bars. At the same time, within the innermost few hundreds of light-years, rotation rises steeply, and small non-circular motions appear, as if orbits there are guided by a deep central mass and by families of bar orbits that twist around it. The balance between ordered spin and random speed therefore changes with radius. Outside, a few thousands of light-years ordered rotation dominates within the box-shaped body. Inside, that random motions climb and hint at a compact core whose gravity presses stars into faster, more tightly curved orbits. Chemistry and age present a third strand. The very center is metal rich with element ratios that imply a rapid early burst of star formation. Several thousands of light-years outward, the light remains dominated by very old stars but carries a mild frosting of intermediate-age populations, likely supplied by gas that drifted inward along bar lanes and rings. This pattern invites a composite picture. A dense classical nucleus formed early when gas collapsed, quickly wrapped by a thickened bar that later gathered and heated disk stars through long-term internal evolution. In this reading, the classical nucleus provides deep central gravity and steep inner brightness, while the bar explains the boxy shape, the near-cylindrical rotation, the straight dust lanes, and the rings that mark special radii. Resonances set the inner geography. An elongated pattern drives gas along its straight lanes toward radii where orbital families change. At the inner resonance, gas drifts into a tight dust spiral and a small star-forming ring wrapped around the nucleus. At a larger radius near the place where the pattern and local spin match the bar hand's material, off to the spiral arms. Andromeda's bright ring at several tens of thousands of light-years fits such a handoff, and the nearly straight dust lanes that meet it match the expected pathway for gas guided along the leading edges of a bar. Ages of clusters along the inner ring and along the outer ring support this scheme, showing bursts spaced as the pattern has swept by and fed gas toward preferred orbits. Orientation matters. If the bar is angled within the plane, one outer arm will appear stronger where it joins the bar, and the near side dust lane will slice the bulge more sharply than the far side lane. Andromeda shows exactly these traits. The slight offset of the bright outer ring from the photometric center can then be read as the lingering wave launched during a past encounter and now trapped near a resonance with the elongated inner figure. In this view, the inner asymmetries, the outer warp, and the lopsided distribution of star formation are not separate quirks. They are linked responses of gas and stars to a long-lived, slowly evolving bar that talks to the disk through resonances and to the halo through exchange of angular momentum. The consequences reach across time. A bar is an efficient engine for trading angular momentum between disk bulge and halo. Stars near resonances are heated vertically and scatter, thickening the inner body into a box. Gas loses angular momentum and drifts inward, feeding inner rings, the dust spiral, and the compact nuclear star cluster. The dark halo can absorb part of the outward flow, allowing the bar to persist for billions of years while still evolving slowly. Over time, the elongated figure may lengthen its pattern, speed may fall, and its vertical thickness may grow through buckling episodes, all without erasing the dense nucleus at the center. Yet tensions remain that keep the debate lively. Some brightness profiles show a steep inner curve that long-term internal evolution alone may struggle to build, while some kinematic maps show more nearly cylindrical rotation than a purely classical bulge would support. The degree of three-axis shape inferred from the twist of the inner contours depends on how dust absorption is corrected and on the exact viewing angle. Small shifts in those assumptions can favor either a stronger bar or a rounder spheroid. The relative weight of the dense nucleus and the thickened bar therefore remains a measured balance rather than a settled fact. Independent traces strengthen the layered view. Metal-rich globular clusters that belong to the inner system rotate with the elongated feature and align along its long axis, while more metal-poor clusters show hotter, less ordered motions that belong to the halo. Bright planetary nebulae in the inner regions map a smooth transition from a rotating box-shaped body to a more pressure-supported central rise, tracing a mass distribution that climbs steeply toward the center, yet remains slightly flattened overall. Even the pattern of microlensing events and the distribution of red clump stars across the inner fields support a mild elongation within the plane rather than a round core. Dust adds both obstacle and guide. On the near side, heavy lanes obscure parts of the bulge and could bias shapes if left uncorrected, but those same lanes outline shocks and streaming that betray the bar. Infrared maps, which see through much of the obscuration, recover the boxy light and the elongated central feature with higher fidelity, while optical maps reveal the patchy inner ring and the curved dust spirals that likely mark resonance and inflow. By comparing these views, observers separate geometry from shadow and confirm that the asymmetries are real structures rather than tricks of extinction. In sum, the bulge of Andromeda is best read as a layered heart. A dense old metal-rich classical nucleus provides deep central gravity. Around it, a stellar bar thickened by vertical instabilities into a box-shaped body shapes, orbits, drives, rings, and maintains mild three-axis geometry. Together they explain the observed brightness profiles, the mix of rotation and dispersion, the dust lane layout, the nuclear and inner rings, and the gentle twists of the inner contours with radius. This interpretation does not close the case. It sets a working frame within which new measurements of stellar motion's dust structure and subtle gradients in element ratios can adjust the balance between the nucleus and the bar. From this crowded, elongated heart, the path narrows still further. Inside the inner ring coils a tight dust spiral and a compact nuclear star cluster whose stars race around a dark central mass that rules the very core. Within the inner few light years, the balance tilts decisively toward the pull of that mass, and orbits become swift and sharply curved. The next step, therefore, leaves the broad bulge and enters the nuclear region, where distances shrink, speeds climb, and quiet light hides the deepest well in the galaxy. At the very heart of Andromeda, light tightens into a compact cluster, whose stars move so quickly that gravity must be concentrated within a span measured in only a few light years. The inner pattern that seemed box-shaped and elongated now yields to a denser arrangement where orbital families twist around a deep central mass. High-resolution images separate the glow into a lopsided brightness, with two peaks only a few light-years apart, a strange double crest that at first suggests two distinct nuclei. Spectra and models resolve the paradox by showing that the stars crowd along an eccentric disk-like configuration that places many orbits near their closest approach on one side, creating a bright cusp there while the true centre of mass sits slightly aside. In this interpretation, a single massive dark object anchors a disk of stars whose elongated paths stack asymmetrically, producing the twin peaks as a geometric effect. Rather than as two independent cores, the central mass asserts itself most plainly through motion. Line-of-sight speeds climb steeply within the innermost arcseconds, reaching several hundreds of kilometers per second, along different slits through the nucleus. The rise is too sharp to be explained by stars alone. Only a compact concentration with millions upon millions of times the mass of the Sun can curve orbits so tightly. Dynamical models that match the velocity field, the dispersion profile and the shape of the light require a central mass of roughly 150 million solar masses, with uncertainties that arise from the tilt and thickness of the eccentric disk, and from how mass to light changes with radius. Independent checks strengthen the case. Gas close to the center shows streaming that aligns with steep gravitational gradients. The inner dust spiral winds inward until it fades at radii where shear and tidal forces overwhelm coherent lanes as expected, near a deep potential well. High-energy sources congregate within the nuclear region, a sign that compact remnants and accretion processes thrive where gravity is strongest. Yet the core is not only a dynamical laboratory, it is also a place with layered stellar ages. Most stars in the nuclear cluster are ancient, their colours and spectral features matching populations older than 10 billion years. Mixed among them, however, lie smaller groups whose light betrays ages of only a few 100 million years, and hints exist of even younger episodes in which gas driven inward by bar torques and spiral shocks collected and briefly formed new stars close to the central mass. These younger components trace faint rings or disks that sit within the older eccentric structure, suggesting that nuclear star formation proceeds in bursts that reflect how gas trickles inward and cools in the hostile tidal field. The presence of young stars so near the central mass highlights a balance between suppression and enablement. Tidal forces raise the density threshold required for clouds to collapse. Feedback from previous generations heats and stirs the gas, and high shear stretches any condensing clump. Only when pressure grows high enough, often in a compact ring at a resonance radius, can gas settle and form stars. Once formed, the stars quickly decouple from the gas and join the orbital families set by the potential, adding their light to the eccentric disk and thickening the nuclear cluster. The geometry of orbits inside the central few light-years differs from that in the broader bar-influenced bulge. Families that loop around the elongated figure outside give way to nearly Keplerian paths near the center, with stars following ovals whose precession rate depends sensitively on distance from the massive dark object. This change in regime produces the observed double peak, and also leads to a wealth of resonant interactions between stars and any remaining gas. Over long times, gravitational encounters between stars and compact remnants, and between the stellar system and the central mass, slowly round off sharp features while maintaining the overall eccentric character. The nuclear cluster therefore evolves through a mixture of collisionless dynamics and gentle relaxation, always governed by the dominant central mass. Dust still plays a role even here. A A thin inner spiral of absorbing lanes winds toward the core and delineates paths along which gas recently moved. In near-infrared images where extinction is weaker, the spiral appears as a faint twist that fades before reaching the center, implying that the final inward step is accomplished more by viscosity and gravitational torques than by clear lanes. Traces of warm molecular gas have been detected within a few tens of light years, thin and clumpy, exactly the sort of precarious reservoir that could feed low-level accretion onto the central mass or seed short star-forming events. The rate at which the central object currently consumes matter is modest. The core shines less brightly than the fiercest galactic nuclei, and its present activity likely fluctuates on timescales shorter than human records. Signs carved into surrounding gas ionization cones, shock fronts extended excited lines are weak, compared with those seen in powerful active galaxies, suggesting that Andromeda's nucleus spends most of its time in a quiet, low accretion state. Even so, the accumulated effect over long spans can be significant. Outbursts, however, mild heat and stir the inner interstellar medium and may help keep the very center pour in cold gas, regulating how often the younger stars can form near the core. The mass of the central object sits on empirical relations observed across many galaxies. More massive bulges host more massive central dark objects, and tighter velocity dispersions in the surrounding stars correlate with larger central masses. Andromeda lies high on these relations, consistent with its bright bulge and with the strong dispersions measured in its inner light. Whether the central object grew mostly through early rapid accretion, through the slow draining of gas along the bar, through the capture of compact star clusters that spiraled inward under dynamical friction, or through some mixture of all three remains a live question. The eccentric nuclear disk itself may be a relic of such infall its stars deposited by a dissolving cluster or by gas that circularized into an offset disk before forming stars. The nuclear cluster also hosts populations of evolved stars whose variable light provides precise timing markers. These variables map the depth of the potential and the mix of ages with a fidelity that complements spectra. Their distribution hints at mild gradients in age within the cluster, with slightly younger mean ages in a shallow ring and older stars more broadly spread. This pattern supports the picture of episodic feeding and star formation superposed on an ancient backbone. The central object influences orbits far beyond the nuclear cluster. Within several hundreds of light-years, speeds and dispersions still carry its imprint, and the inner ring of gas appears to lie near a resonance set by the elongated pattern and the central mass together. Gas driven inward by the bar may queue at this ring until pressure or shocks allow it to cross the final barriers and flow closer to the core. When it does, a brief brightening and high-energy emission may result, after which the system subsides again. Over many cycles, such events could build the observed central mass and maintain the nuclear star cluster without ever producing the wild output of a quasar. In this compact realm, the theme of the whole galaxy repeats in miniature. An invisible scaffold determines motion. Dust and gas write a changing script. Stars form in pulses and then join the steady background, and a central mass regulates the pace without declaring itself through spectacle. The approach, which began in the cool outskirts of the halo and moved through streams, satellites, disk warps, arms, rings, and the box-shaped bulge, now stands at the inner lip of the deepest well. The final inward step will look directly at the central mass and the surrounding orbits with the sharpest available measurements, weighing how closely the crowded heart adheres to a simple point mass picture, and where subtle departures hint at the grain of the nuclear disk and at ongoing quiet feeding that keeps the core alive. Destiny enters the frame not as a sudden event but as a long unfolding whose first act has already begun. Andromeda approaches the Milky Way along a line only slightly tilted from centre to centre, a quiet drift that adds several hundreds of kilometres per second to the local flow, and that will over spans measured in billions of years draw the two spirals together. The background expansion of space does not prevent this, because within the local group gravity from the combined dark halos wins. The timing argument set by present separation approach speed and the age of the universe outlines a schedule with wide sleeves for detail and a firm shape for the whole. First comes the era of deepening influence. Long before the bright disks touch the outer halos already overlap, and their tides work upon satellite streams and outer gas. Paths of small galaxies bend, thin planes wobble, and the outer warps of both spirals twist a little more. Filaments of hot halo gas begin to mingle and ram. Pressure grows on dwarfs that pass through the saddle between the giants. From far within each disk the sky would still appear unchanged, yet the realm of the outskirts has entered a shared weather. As distance closes to several hundreds of thousands of light years, tides begin to draw faint bridges of stars and gas between the two systems. The first close passage follows not a headlong crash, but a sweeping flyby that launches waves through both disks. Gas compresses along broad arc star formation rises in rings and crescents, and long tidal tails peel outward. The exact geometry of this first encounter depends on small angles in the present approach and on the rotation directions of the two disks. If the spins are roughly aligned with the orbit tails and bridges grow more grand, and star formation rings strengthen. If more misaligned, the pattern thins and twists into lopsided wakes. Either way, the first pass leaves both galaxies' altered bars lengthen or awaken spiral patterns. Change phase and central inflows increase as torques rearrange angular momentum. A pause follows that is long on human scales and short on cosmic ones. Friction from the overlapping halos and from tides drains orbital energy. The systems separate, then fall together again on a closer path. During the interval, bridges fade, tails extend, and new clusters light up along compressed ridges. Some satellites are captured by the partner halo, others are flung outward on wider tracks. Streams in both halos thicken where they cross, and the map of background galaxies behind the pair carries a slightly stronger lensing signature as the mass grows more concentrated. The second approach reaches deeper. Now the bright disks strike through one another's outer parts, and waves reach closer to the centres. Gas driven inward by bar torques and tidal shocks pools into inner rings where brief starbursts flare. Central masses feed at slightly higher rates, brightening in high energy bands for short episodes. The box-shaped bulge of Andromeda and the barred heart of the Milky Way respond by heating further and by handing angular momentum outward, while the dark halos absorb part of the orbital spin. The combined figure that emerges after this second pass is no longer two neat spirals with separate identities. It is a double core wrapped in overlapping envelopes, turning within a shared halo whose centre lies between the former galaxy centres and moves slowly toward their mass-weighted mean. Over another span, dynamical friction brings the cores together. The orbits of stars that once belonged to thin disks puff into broader distributions, and the bright body begins to resemble a spheroid with shells and ripples that mark the last close passages. Tidal tails, once narrow and sharp, fall back as long streams that wrap the remnant. Globular clusters from both systems mix into a larger, more populous family with a broad distribution in metallicity and a wider range of orbits. Some clusters sink toward the centre and dissolve, feeding the nuclear regions. Others are flung onto distant paths that trace the far halo. The final coalescence of the two central regions brings the pair of massive dark objects into a bound binary. At first, the separation is measured in hundreds of light-years, then in tens, then in fractions. Stars passing near the pair carry away energy and angular momentum tightening the orbit. Gas, if present in sufficient amounts, forms a circumbinary ring and torques the pair inward further. When the separation falls small enough, the emission of ripples in space-time takes over, carrying away the last angular momentum and bringing the two masses together. The merger releases a burst of gravitational waves that races outward through the local group, too small to disturb any star yet strong enough to be calculable by future instruments. The combined central object settles with a mass that is the sum of the two minus a modest amount carried away by the waves, and it receives a small recoil kick that could displace it briefly from the photometric center before dynamical friction draws it back. The remnant galaxy that forms is likely to be a large, slowly rotating spheroid, with a broad envelope and a dense central rise often called an elliptical, though the exact label depends on how much of the disk survives. Some simulations suggest that a small renewed disk could grow later if gas from the outer regions continues to cool and fall in, leading to a profile with both spheroid and disk components. The stellar populations will show a mix of very old stars from both progenitors, intermediate age stars formed in merger-driven bursts, and younger stars in any regrown disk. Shells and faint ripples will persist for billions of years as memories of specific passages gradually fading as orbits mix. Planetary systems ride through this drama mostly untouched in a direct sense, because the distances between stars are so great that direct collisions are exceedingly rare. The night sky from a world within either original disk would change grandly as the partner galaxy swells and then spreads across the heavens, but local gravity would remain set by the nearest stars and by the total mass of the remnant. Gas dynamics, however, could reshape long-term prospects for star formation in such a system. If much gas is consumed in bursts and much is heated into a hot halo during the merger, the long tail of star formation may dwindle, and the remnant may age into a redder, quieter galaxy, if cooler streams continue to feed the remnant and if a disk reforms a gentler ongoing pace could persist. The triangulum spiral adds a thread of uncertainty that widens the range of possible paths. If bound tightly, it may join the dance early, making a three-body choreography in which its tides alter the phases of the main passages and seed extra star formation in arcs and rings. If only loosely associated, it could arrive later and merge with the remnant, adding a fresh round of ripples and renewing the outer envelope. Its own satellites and streams would then mix into the larger halo, increasing the richness of the final cluster system and adding new planes of debris that slowly dissolve. Throughout the encounter, dark matter remains the stage rather than the actor. It absorbs angular momentum, sets the broad shape of the potential, and allows the visible parts to rearrange while keeping the total system bound. The mass-to-light ratio of the remnant rises further in the outskirts, as more of the total mass sits in the dark halo, and as the outer luminous density falls. Weak lensing of background galaxies by the remnant would show a slightly rounder, more centrally concentrated profile than the sum of the two progenitors did separately. The timescale for all of this is long enough that many cycles of the Sun around the Milky Way would pass before the first strong passage, and many more cycles would pass between passages. Across that time, the quiet procedures described in earlier sections continue. Inside each galaxy, dust lanes build and disperse, rings, drift bars trade, angular momentum clusters light and fade, and streams unspool in the halos. The merger does not erase these processes. It gathers them into a larger frame, and lets their signatures write upon a shared canvas. The story of the future encounter therefore resembles the story of the present structure, steady forces acting over long spans, punctuated by episodes of stronger change that leave ripples and rings. The final form will be a composite memory, a system whose smooth light hides layered histories that careful maps can still recover. With this forward view set, the narrative now releases its hold on motion and returns to rest, ready for a quiet wind down that lets the weight of scale sink gently into calm before sleep.